Good evening, ladies and gentlemen. Can you all hear me out there? Okay. How's that? Any better? Better? Check, 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 check one. Yeah? How's that? All right, cool. Well, how's everyone tonight? That better? Yay. Well, this is the biggest packed house I think we've had all season, so thank you all for coming out tonight. We're grateful. Launched in 1977, the twin Voyager spacecraft were assigned an ambitious mission to explore the giant outer planets. Both spacecraft flew by Jupiter in 1979 and Saturn in 1981. Voyager 1's flight path at Saturn bent away north of the ecliptic plane, while Voyager 2 continued on to encounter Uranus in 1986 and Neptune in 1989, then had its path bent south of the ecliptic. Both spacecraft are now heading out of the solar system with enough onboard resources to continue sending data until at least 2020. In 1998, Voyager 1 became the most distant human-made object in space, and in August 2006, it crossed into a region at the outer edge of our solar system and could cross into interstellar space beyond the sun's domain within the next 10 years. Tonight's guest speaker graduated from Rice University with a BA in physics in 1966. He attended Churchill College in Cambridge, England from 1966 to 1967 as a United States Winston Churchill Foundation Fellow, then went on to earn a PhD in physics from the California Institute of Technology in 1973. Since that time, he's been employed in the Space Radiation Laboratory of Caltech, where he is presently a senior scientist and member of the professional staff. His research interests have recently centered on studies of the anomalous cosmic ray component, while currently he is analyzing data returned from the Voyager 1 spacecraft, which is beyond the solar wind termination shock, and from Voyager 2, which is close to the shock but still upstream of it. He is also the co-author or author of more than 70 publications. He is a co-investigator on the Voyager Cosmic Ray Subsystems experiment and on the Advanced Composition Explorer mission, and he has also been the instrument manager for 5 instruments, 2 on the SAMPEX mission launched in 1992, 2 on ACE, which was launched in 1997, and 1 on Stereo, which was launched in October 2006. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Alan Cummings.
Well, thank you very much. Thank you for coming out on a night when Are You Smarter Than a Fifth Grader is on television. I know that's a big sacrifice. It is, if it makes you feel any better, it is for me too. That was a very nice introduction, Mark. I appreciate that, but there's just a few things about me you need to know, I think, in order to understand and enjoy this talk. I want to start with that slide. This is me. This is without my coat and tie on. I got my boat shirt on. I run about 5'9" high, but I tend to exaggerate a little bit, so let's make that 5'8". I come in at about 155 pounds. I grew up in Texas. Now, Texas is way bigger than that. Yeah, that's better. Okay, as he said, I arrived at Caltech in September of 1967, and I've been working there ever since. I've never left even the group I'm in. So we're celebrating today 30 years of Voyager in space and 40 years for me at Caltech, and I don't know which is more improbable. This is the picture of me on my homepage. I've had the mustache since 1972, since Voyager was approved as a mission, as a matter of fact. And I like this picture because the mustache is still dark. Okay, well, we're here to celebrate the launches of Voyager, and I can remember when they're launched because they're engraved on the back of this nifty belt buckle. I've had this belt buckle since the time of launch. Anyway, Voyager 2 was launched on August 20th, 1977, and Voyager 1 was launched later on September the 5th, 1977. They decided that the first spacecraft to Jupiter gets to be named Voyager 1, and it went out second on a faster trajectory. Now, when I got that belt buckle, it replaced my most cherished possession, my Texas armadillo belt buckle. And the other day when I was rummaging around in my closet to try to find a belt for this event, you know, I have one of those belt racks. It's circular and it's run by a battery. Well, the battery's been dead for 5 years, but I reached around behind and I pulled out this, yet another Texas armadillo belt buckle. So I immediately realized I have a problem. I've got some sort of obsession with Texas armadillo belt buckles. But don't worry about me. I'm going to be fine. I've checked into rehab. I've entered the Texas Armadillo Belt Buckle Rehabilitation Center. It's right over here in Pasadena, and they let me out to give this lecture. So far, I don't feel like it's made any difference, but we'll give it some time. Now, as I said, I've been here since 1973 working on Voyager. As soon as I got my PhD, that's me bent over there. You see, I was the only one in the group that could read the data upside down. This is our very first data from Voyager 2 right after it was launched. And we're all trying to contemplate what all those numbers mean. Now, Voyager's been called the greatest mission of exploration in the history of mankind. And I fully subscribe to that notion. And I'm very honored to be here to share some of the history of Voyager and some of the highlights of the mission to date, and to look to the future because the mission's not over yet. Voyager is exploring the frontiers of our solar system as I speak. And I'm also a bit petrified because not only is there a big audience here, but this is also being webcast, and as Carl Sagan might say, billions and billions of people could be watching. It's not likely, but it's not impossible. So I stand here representing thousands of people that made Voyager possible. Some are probably in this room tonight. Lots of incredible engineers and technicians at JPL and wherever they build the rockets. Just amazing. Even politicians made a difference in this mission, as we'll get to in a minute. But tonight I want to just highlight a couple of people that made this mission possible or had something to do with making it possible, even though they didn't work on Voyager as far as I know. The first one is Mike Minovich. Mike Minovich was a graduate student from UCLA, worked a summer job at JPL in the early 60s, and he discovered that if you send a spacecraft past a planet, you can get a speed boost. And it turned out that this would be very important for Voyager because it would cut the time down to get to Neptune from 30 years to 12 years. So he was a discoverer of the gravity-assisted interplanetary travel. And that was a picture of him at the Neptune encounter, one of the Neptune encounters on the right. The other fellow is Dr. Gary Flandreau. He was a graduate student also, but he was from Caltech, and he was working at JPL also in the summer. And he was building on Minovich's work, and he discovered that there was going to be this rare alignment of the outer planets that would enable the Voyager mission, that you could go from one to the next, getting a little speed boost as you went along. And they were all lined up, and he found out that this only happens once every 176 years. And so it was going to happen in 1977. And the last time it happened was, like 1801, and Thomas Jefferson was president. And Thomas missed his chance. Now, Thomas, had he known he had the chance, and if he had any, the technology to do anything about it, I'm sure he would have done it because he was a scientist kind of a guy. So who was the president that didn't miss his chance? That was Richard Nixon. And I've been told that they actually went to Nixon and told him that Thomas Jefferson missed his chance, and you don't want to do that. And he signed off for it. He said, go for it. I think it's just amazing that the technology to do this mission and the alignment came along and discovered the gravity-assisted interplanetary travel. All that came together just at the right time to make this mission happen. And I think it's interesting that a couple of graduate students doing summer jobs really helped make it possible. Okay, so the developments were that the NASA immediately seized on the obvious and said this mission has to be done. And so the Grand Tour mission was approved. In fact, they were going to visit all the planets, including Pluto. Pluto wasn't lined up right, so it was going to take another spacecraft to do that. But then the budget reality set in. This was going to cost a lot. The Vietnam War was raging, the Apollo missions were going on, and Space Shuttle was coming on, taking a lot of money. So the Grand Tour mission was canceled, despite everything I just said about missed chances. But JPL was not to be denied, and they immediately came up with a new mission called MJS-77. It's Mariner, Jupiter, Saturn, launch it in 77. And Mariner was a class of spacecraft at the time. And it was just going to go to Jupiter and Saturn, and that's it. There was going to be 2 spacecraft. And Uranus, Neptune, and the interstellar mission, which is what we're in now, all got approved after launch. Okay, so this is the development. This was actually the backup plan at launch. if Voyager 1 had not had a successful mission to Jupiter and Saturn, hadn't done a good flyby of Titan, one of the Saturn's moons, then Voyager 2 would have been programmed to do exactly what Voyager 1 did. It was a backup for that. But since Voyager 1 did a great job, Voyager 2 was programmed to target these planets so they could do the grand tour and do all the outer planets. I can say that now since Pluto's been demoted. No longer really counts. You notice, now Mark said this earlier, but at Saturn, Voyager 1 was targeted in such a way that it deflected up out of the ecliptic plane, and Voyager 2 got deflected down after Neptune. And actually, you know, they're going sort of toward in the same direction of the heliosphere, except that they're one's up and one's down, and they're actually quite far apart in real distance. Okay, so this is the spacecraft that got built, and for you here, you can look right over there. This is a picture of that full-size mock-up. The first thing you notice on here is this dish antenna, and that's 12 feet across. So that's like 2 of me. Well, as you know, I'm not quite 6 feet tall, so let's put a little bit more of me in there. And, but if you're like me and you need a completely different kind of measuring stick, it's 7.5 armadillo lengths long. Now I'm using, I know there are lots of different kinds of armadillos, don't get me on that. I'm using the 9-banded armadillo that we're all familiar with. Now if you're ever on a quiz show and they ask you how big the dish antenna is on Voyager, you'll never forget that. You know, if they tell you, is it 12 meters or is it 12 feet, you'll know it's 12 feet. So just send me half the money you win for that. Now, how big of a light bulb do you need to stick in that transmitter there to communicate with Voyager? Voyager 1 right now today is 103.92 AU away from the sun. Let's round it up to 104. 104 AU. And you know what AUs are. By this time, you're probably thinking armadillo units, but now, that would be some mighty big armadillos. There's only 104 of them stretched from here to Voyager 1. AUs are astronomical units, and 93 million miles is the distance from Earth to the sun. And so 104 of those is 9.7 billion miles. And that's a long way. And so it turns out, though, that this dish antenna communicates with the Deep Space Network's 34-meter dish antennas here on Earth using a 23-watt power source. No bigger than a refrigerator light bulb. I think it's just amazing that we can communicate with Voyager. And it turns out that that's not the limiting factor at all. If we had more power, we could go a lot further with communication. But the power will run out first. Let's see, the other things you notice on here are the power source, which are these RTGs, which stands for radioisotope thermoelectric generators. That's just a radioactive, big plutonium radioactive source with thermocouples that get heated up by the radioactive decay, and then that's your power. It was a little over, I think, 400 watts at launch. It's down to a little under 300 watts now. It's slowly decaying away. There's also the golden record, which has on it the sights and sounds of the Earth, and also instructions for the aliens in case they pick it up to find us. And I hope the aliens know that if they're going to want to get in here, they're going to have to follow our strict immigration procedures. And if they want to get into JPL, they're going to need a badge. They're going to need to submit to a background check, and I would like to see that. This is the science boom where most of the science instruments are. And I got another slide that shows those. The imaging science had 2 cameras, a wide angle and a narrow angle camera. There's the ultraviolet spectrometer, the infrared spectrometer, there's a photopolarimeter. And the instrument I work on is the cosmic ray instrument right there. And among other things, you know, I forgot something. I forgot to tell you that I got those belt buckles up here, if anyone wants to see them after the show. Now, I also have up here one of these things. This is a low-energy telescope from that cosmic ray instrument that I assembled about 16 of these, 4 for each. There's 4 of them that stick out the top of that cosmic ray instrument there, looking in different directions. And so there's 2 spacecraft that were 8. There's actually 3 spacecraft that we had to make. One was the proof test model, and then there's a spare. So if anyone wants to see real space hardware after the presentation, you're welcome to come up and take a look. There is also the, man, I got these 2 things. Got to keep it straight. The low energy charged particle experiment. There's the planetary radio and plasma wave experiments using this antenna. The magnetometers are on a separate boom, which is 43 feet long. It has 2 magnetometers on it. And then there was another science experiment just using the radio signal itself from Voyager. And yeah, I'm glad I had that come on there because I was afraid I would forget that. There are 3 computers running this spacecraft, and each has 8K of memory. That's not 8 megabytes, that's not 8 gigabytes, that's 8,000 bytes. And I was just told by Jeff the other day that actually right now they only use half that memory. It's amazing what they do with running this spacecraft. Okay, so these are the target planets. These are shown in the proper size compared to the Earth. You've got Jupiter, Saturn, Uranus, and Neptune. And the great red spot there, Voyager proved, was a giant hurricane that's been raging for probably over 300 years. And it takes 2 Earths to fit in there, so that's a pretty big hurricane. In January of '79, the Voyager images of Jupiter were better than any ground-based photos. So this was taken, these are 66 photos run together in a movie. And notice this hurricane is gobbling up these little white hurricanes. You can see that they run, this first one here, there's a little white one here that runs by, and he makes it out the backside. He's all right. The next one, though, whoops, not so fortunate. Going back around. So it's quite an atmospheric system on that planet. Now this is the picture that gave me chills when I first saw it. I remember that day very distinctly. I went over to Ramo Auditorium on the Caltech campus, and they had a video feed, and this was up on the screen. And I swear that I thought Caltech students had pulled a prank. They had put a picture of a poorly made pizza up on the screen. And, but it is no pizza. This was the Io moon of Jupiter. And it was so different than what I expected. I think a lot of people at the time, thought, well, going and taking all these pictures of all these moons, this could be kind of boring, because I think they might just look like this, you know, Earth's moon. That's our example. But boy, were we wrong. This was quite different. And while we were all studying that, or the proper people were studying why there were no craters on this thing, and how smooth it was and all these spots, Linda Morabito of the navigation team, she's now Linda Morabito Kelly, was overexposing a part of this image to try to find a background star to navigate by. And she discovered this, a volcano that was actively going off at the time. It's a blow up there. It turns out this was really a big surprise. No one really, people expected some tidal heating to be going on, but no one expected active volcanoes on Io. And it turns out that Io is 100 times more active volcano-wise than the Earth. The tidal motions of the surface are by 330 feet. And that creates a lot of heat internally. And then that spews out sulfur and oxygen and other things. In fact, the cosmic ray instrument I worked on, or I'm working on, measured lots of sulfur and oxygen in the magnetosphere that was accelerated up from about 2,000 miles an hour, which came out of there to about 67 million miles an hour, a tenth of the speed of light. Now this is a crater on Io that was taken by Voyagers, and it's about 30 miles across, very big. And it's one of those pictures where you start looking at it and you start thinking you see something. Don't you think that looks like the head of a dog? I mean, there's the nose, there's the eyes, there's the ear, and I think I see something else. Let's zoom in that ear. Yeah, it's an armadillo. That's what I thought. Maybe it's not a belt buckle problem, maybe it's an armadillo problem I've got. Maybe I'm in the wrong rehab center. Then came Europa. Europa is another moon of Jupiter, and it's what I call the cracked cue ball. We're up to 63 moons now on Jupiter, and Voyager discovered a lot of them. A lot of them are small and irregular. One of them, though, is the biggest moon in the solar system, Ganymede, and it's the only one with its own magnetosphere. But here we have Europa, and I've got another picture, a little more of a close-up, showing all these cracks. It's very smooth. There's nothing over about 300 feet in elevation on this whole surface. And it has, they think, 2 times the amount of water that Earth has. And it's underneath this frozen crust here. And they don't know exactly how deep that is, but it's very intriguing that there could be life down in that water underneath. It's pretty cold. You know, it's very cold there, but still, down in the liquid water, it wouldn't be so bad. Okay, Voyager discovered that Jupiter had rings. And it turns out now, of course, all the planets, all the outer planets have rings. And this is the champ in that department. This is Saturn. This is a view you can't see from Earth because it's Saturn in eclipse. This was taken by Voyager 1 after it passed Saturn. And the closer we got to looking at the rings, the more rings there were. They just were finer and finer divided. Now, this is the F ring that Pioneer 11 actually discovered this earlier, but what Voyager discovered that there were two little satellites, Prometheus and Pandora, that shepherd this ring and make it where it is. And in fact, the gravitational interactions are such that it looks like it's braided. So that was a big surprise as well. And here was something Voyager discovered. Voyager discovered there's something peculiar about these rings. And let me see if I can get this movie going. Yeah. The rings have spokes. These are radial dark spokes on the rings that, as far as I know, are not fully understood today. They are thought to be dust, I believe, levitated above the rings by electrostatic forces. And then there was Enceladus. That's a moon of Saturn. And Enceladus is about 300 miles across, and it's actually the subject of the von Kármán lecture last month, so I don't need to go into that. But they found Cassini is orbiting Saturn and found that this moon has a big geyser going off on the South Pole. And you can see that it looks very active. There are craters, all right, in some places, but there's a lot of smooth areas where stuff has melted and flowed and stuff like that. And then there's Iapetus. This is really bizarre. This is half charcoal black and half white as snow. You can't tell on this photo, but this is very white, this is very dark. It's just half and half. And if you want to see some really amazing close-ups, early September, Cassini got really close to Iapetus. And if you go to the JPL Cassini website, you can see some pretty interesting photos up close of this moon. And here's a moon that's lucky to be with us. This is Mimas. Mimas got hit. It looks like the Death Star from Star Wars. In fact, it's got the same dimensions. They say that's just a fluke. But this little, if it had been any bigger at all, this moon would have shattered. There's even, I think, a crack on the back which propagated through. And this is about the size of Mount Everest, that little peak in the middle there. Then came Titan. When Voyager was launched, Titan was thought to be the biggest moon in the solar system. But Voyager got there and said, oh, lots of atmosphere, much thicker atmosphere than we thought. So thick, in fact, can't see anything. So that was a disappointment. But there's an interesting thing about Titan. So anyway, it's now the second largest, because the interesting thing about Titan is that the gravity, surface gravity is low. It's about 14% of that of the Earth. And the atmosphere is dense. It's like 1.5 times the pressure at the surface as Earth. So you could just strap on some wings and you could fly around there like no tomorrow on Titan. Now you may have trouble breathing that atmosphere. It's 98% nitrogen. And it's cold. You'd freeze straight to death. It's 290 degrees Fahrenheit below zero. I couldn't resist showing one photo from Cassini in this regard because we didn't see anything on Voyager, but Cassini launched a probe, Huygens probe, that landed on Titan, and this is what they found. I think they found Palos Verdes. See this? It's got rivers, it's got gullies. It turns out, even at minus 290 degrees Fahrenheit, it can sustain, it has lakes and rivers of methane and ethane, unfortunately. This actually is a plain. It is not a shoreline like we first thought. This is actually where Huygens ended up landing. Okay, Uranus. Uranus was somewhat bland, but it has a very interesting property. Uranus is a planet that is tilted on its side. Its rotation axis is horizontal, like in the plane that it revolves around the sun. And that's opposite of most planets. All the planets have the rotation axis up and down with respect to rotating around the sun, or revolving around the sun. But not Uranus. And The other thing that's peculiar about it that Voyager found was this magnetic field. This magnetic field it has is offset by like 60 degrees from the rotation axis. We've never seen a planet that didn't have the rotation axis and the magnetic axis somewhat aligned, a lot better than that. And the other interesting thing about it is that the center of the magnetic field is not in the center of the planet. It's offset by about a third of the planet. So that was very bizarre. And here is one of the strangest moons in the solar system, Miranda. It's about 300 miles across. It's small. It should have just frozen solid in place when it was formed and should be just full of craters and nothing should be happening. But it's not. It's got lots of character to it. And that was one of the things I think Voyager really discovered was all the diversity. It didn't look like the moon. None of the others looked like the moon, really. And here's some close-ups that Voyager took of Miranda, showing some, it looks like they've been plowing the fields over here, you know. Turn that corner. Chevron shapes. Very bizarre word. I don't think it's really understood totally how this came to be. And then there was Neptune. Neptune is at 30 AU, it gets 1/900th of the sunlight that the Earth does. It gets 1/36th the sunlight that Jupiter does. And so you wouldn't think it'd have much weather on it. But in fact, it's got this great dark spot. It's got other little storms of some sort here. And in fact, it has the highest winds in the solar system, 1,500 miles an hour, which is 10 times a Category 5 hurricane. So it's not really understood why there's enough heat inside to do all that. Now, it turns out this great red spot, great dark spot, was there when Voyager went by, but it has since disappeared. So it's a dynamic place. It's not like the great red spot, which lasted at least 300 years. Now, Neptune also has this property that its rotation axis and magnetic axis are tilted by quite a bit, 47 degrees. And it sets the record for having the center of the magnetic field offset from the center of the planet. It's by more than halfway to the surface. Then came Triton. Triton is a pretty good sized moon, 1,700 miles across, and it's really odd because it's orbiting Neptune backwards. It's a retrograde orbit. So it didn't form in place along with Neptune. It's a captured Kuiper Belt object, undoubtedly. And it's also extremely cold. It's the coldest big place in the solar system, 35 degrees Kelvin. And I think you can see here that despite how cold it is, it's active volcano-wise. It's got geysers of volcanoes going off. You see these black streaks and this big plume. I'm going to show you in a minute a movie of one of these things is actually going off when Voyager went by. But first I want to remark upon this Y over here. Doesn't that look like where the 5 and the 405 meet? Yeah. Well, I think if the Tritons can get their car started in that cold air, I hope they can solve the Y problem for traffic congestion better than we have. Okay, this is the movie that I'm going to hope you can see. It's pretty tough, but we'll try it. Anyway, there you go. So there's a geyser going up here, and it goes up about 5 miles, and then it catches some wind, and it goes downwind about 90 miles. And that was photographed just when Voyager went by, Voyager 2. Oops, did it again. Okay, so this photo montage ends the planetary portion of the mission. Voyager took tiny points of light in some places and gave them real places. And I think it was just amazing the diversity that Voyager discovered. But what's next? What's next is the Voyager interstellar mission. So what's that? Interstellar means between the stars like the stars in our galaxy, the Milky Way galaxy. And right now, the two Voyagers are in a region of space that's dominated by the sun. The sun's the boss. The sun's spewing out a solar wind, which is blowing a bubble in the galaxy, which we call our heliosphere. And all the low energy solar wind particles and everything are coming from the sun. We want to get Voyagers out beyond that bubble into interstellar space, into the galaxy, and explore a new environment for the first time. Now, it turns out that a couple of things have to happen. One, the Voyagers have to keep going, and that's going to happen. There's nothing that can stop them. Even if the RTG power went out, the power has nothing to do with the fact they're just coasting along anyway. So they will coast forever. And then it turns out in the case of Voyager 2, in 40,000 years, Voyager 2 will be near a different star than the Sun for the first time. But we don't have to wait 40,000 years to get to the edge of the heliosphere. But we do need to spend a little bit of time here understanding the structure of the heliosphere. And we're going to start by looking at our place in the galaxy. This is the Sun. This is our Milky Way galaxy. We're out here on the Orion arm. We're about 8 to 10 light years from the center of the galaxy. And if you zoom in and go a little closer, you can see here's the Sun and its direction of motion about the center of the galaxy. Here's the direction to the center of the galaxy. Here's Alpha Centauri, a pretty close neighbor at 4 light years. And this is the motion of a local interstellar cloud. This is material from an exploded star that happened millions of years ago and is kind of drifting this way. And these two motions, the motion of the Sun this way and this way, makes that bubble that I talked about not be a sphere, but be kind of like a windsock in the galaxies. It's shaped by these winds. Now I'm going to show you the solar wind, sort of what's going on here with the solar wind blowing this bubble. This is a picture from SOHO, and this is the Sun behind that blue circle there. The little circle is about the size of the Sun, and the bigger circle is there to keep the camera from being obliterated by too much light. I'm going to play a little movie now, and this happens to be a time when a comet comes by, and you'll also see this, you can see the outer atmosphere of the Sun blowing out. Okay, so here comes the comet, and you can see how that comet tail tries to stay radially out, and that's the solar wind doing that. You also could see that there's a kind of an explosion. You could play that again. It's going along in pretty good shape, and then boom, and another one down there. And so this happens fairly often at certain times and leads to a lot of turbulence in the heliosphere. Now I'm going to play a movie where you're near the Sun and you're going to travel out and you're going to look back, and if you had magic vision, this is what you would see. So you're going out here, you go past planets, there's the Earth whipping by, and you can see the orbits. There's your magic vision for sure. But you can see the Sun is blowing out this supersonic solar wind, and as it goes out, it loses its pressure decreases, and it comes to an abrupt transition to a much lower speed right here at this, what's called the solar wind termination shock. And that's this inner circle. Now, in order to get to interstellar space, we need to get out beyond this next boundary called the heliopause. This is the great divider between low energy charged matter from the Sun and low energy charged matter from other stars or remnants of other stars. And so we're trying to get to that boundary there. There's also another structure probably called the bow shock. I mean, it's called the bow shock if it's there, and it probably is there. This was just a cartoon drawing, but these, whoops, try that again. Oops. Okay, now this is what I want to show next. I was just going to show you could make a heliosphere in your kitchen sink. This is an analogy. It's not a real heliosphere. It's a two-dimensional flat analogy to one, but it's very much similar to the phenomena that we're describing. And I'm going to warn you right now that these labels I've got on here, here's solar wind. See, the Sun is represented right there where this water is going to be rushing out radially in all directions. That's what happens at the Sun. The solar wind blows out like that. And then it loses its ability to hold off the water around here, builds up this ridge, and this is the heliosheath, interstellar space beyond that. And when it gets to the heliosheath, the water turns and runs down the sink, down the tail of the heliosphere. That's very similar to what we have. Now, what I want to warn you about is those labels are going to get covered up as soon as I play this movie. I know there got to be fifth graders out here in the audience that could have told me how to do this right, but I didn't get the job done. So we'll play this movie. And you can see the thing you see here is how turbulent things are. Things are not a steady flow, and that's the same on the Sun. So the termination shock is kind of in motion, but you can try that at home. Okay, now here, back to this picture where I've got some labels on it. It shows the termination shock there. This is where Voyager 1 is. Voyager 1 went through the termination shock recently in December of 2004. Voyager 2 is zeroing in, getting close to the termination shock. And this is the target. This is the place we're trying to get to, the heliopause. And out beyond there, we'll be measuring a different environment than we've measured before. Now, that was just a cartoon drawing, but there are real astrospheres, what they're called, around other stars. And this is a Hubble photo of the Orion Nebula, and it shows a star with this bow shock and swept back like that. And if you look up here, you'll see not another armadillo, but another astrosphere. So now, as I pointed out, there are these explosions on the sun, or these coronal mass ejections was what they're called, and it means a lot of stuff is coming out real fast. And that causes, this is a model of those, what happens when those disturbances come out from the sun. Whoops, sorry about that. I got to play the movie. So this is by Gary Zank, and I keep doing that. That's not, whoa. Wow. Okay, that was exciting. Just don't hit the wrong button. You know, these left-hand, right-hand things. The disturbance comes out. You know, earlier when I did this, it plays for longer than that. But it makes this termination shock move back and forth, and it propagates all the way out to the heliopause as well. And it turns out when it gets to the heliopause, it makes radio waves that come back in and have been detected by the Voyager spacecraft. And that's shown here on this plot. This is frequency of detection along this axis. This is time of the year along this axis. And the intensity is in the color, and red is the highest intensity. So the biggest events were 1983, 1984, and then 1992, 94. And there's a small event in 2002, 2003. In fact, recently there's been some other small events as well. And by knowing when the disturbance left the sun and when it passed the spacecraft and when these were detected, they've been able to estimate the distance to the heliopause. Now, I don't know where you were on this night. This West Wing TV episode was shown, but here's a quote on the show. Josh, I need a breakdown of NASA funding as a percentage of discretionary spending in 5-year increments starting in 1969. Hey, you want to hear something cool? Voyager 1 just crossed the termination shock 8 billion miles away. First human-made object to leave the solar system. Now, that was from a West Wing episode of 11 February 2004. Unfortunately, we actually crossed the shock on December 16th, 2004, 10 months later. But that's not their fault. I mean, there was a lot of confusing things going on when we were looking at that data early on. We were very appreciative to get the support of the administration, even if it was the fake administration. We'll take it. And how we got mixed up with Genghis Khan, I don't know. But again, any publicity is good publicity, I think. Now, this is some of the evidence for the crossing of the shock by Voyager 1. This shows, this is counting rate going up and time going across, and these are different energy channels of the detection by the charged particle experiment, low energy charged particle experiment. These things marked TSP 1 and 2 represent times when we were getting particles from the termination shock, but we weren't at the shock yet. I'll show you that a little bit later how that works. But right here in December 16, 2004, my son's birthday, that's why I'll never forget this date. We crossed at 94 AU, and the intensity just jumped up and they got real steady as compared to all this jumping around and lower intensity. So that was one indication. That wasn't the critical one, though. The more definitive one was the magnetic field. I told you the solar wind is coming out from the sun. Well, embedded in the solar wind is the sun's magnetic field. And as it gets to the termination shock, you have a sudden slowdown of the solar wind, and that means the magnetic field gets compressed, and so the strength goes up. So what we're going to show in another movie is this magnetic field strength along this axis, low to high, and this is time of the year. Now, we cross about right over here, right into 2004. So we're going along in the light blue, plodding along, and then suddenly right here jumps up, and we get this increase. This was really the definitive signature that we were looking for. Now, you can't tell on this plot, but there's something interesting about this period. You know, Voyager sends its data back all the time, but the antennas on Earth are not tuned to it 24/7. The antennas get busy with other spacecraft. They can't look at it all the time. And so, but they do a pretty good job. We get about half the data from Voyager 1. If we don't get the data, you know, the data just streams on by the Earth, and, you know, aliens on the other side may be getting it, I don't know, but we're not getting it. And, but they, you know, about half of the data on Voyager 1 we get, about less than that on Voyager 2. Actually, Voyager 2 is in the south. There's only one antenna in Canberra that can look at it anyway. So the maximum you get is about 12 hours, and we get a lot less than that. But every day of the year in 2004, we got data. They got some data on every day except the day we crossed the termination shock. That was the only day all year that we didn't get data. So we didn't really see the crossing in real time. We observed what happened on December 15th and what happened on December 17th, and we inferred that it happened on December 16th. Now, if you want to know when Voyager 2 is going to cross the shock, I think you just need to find out when the DSN is not going to cover Voyager 2, and that'll be the day. Now, just like the planetary encounters were full of surprises, so was the leading up to the termination shock and being in the heliosheath have produced a lot of surprises. And this is just one example from the magnetic field. This is magnetic field strength, and these are days across here. So this is one set of about 5 days and so forth, different set of days. What they found were the magnetic field is going along. It should just be up here like this, and all of a sudden it almost drops out to zero. There are these dips, magnetic holes they call them. That was unexpected. But one of the biggest puzzles has to do with something called the anomalous cosmic rays. And if you heard the introduction, that's what I enjoy studying. So you're going to get a little dose of that right now. Anomalous cosmic rays are thought to begin their life as interstellar neutral atoms. In that cloud that's blowing by has got neutral atoms in it. And these atoms have all the electrons around the nuclei, so they don't have any charge. And those guys, they don't care about the magnetic field. So they come right on in. They're not affected. And they come in, but when they get close enough in here, the sun is putting out the solar wind, and that could knock an electron off, or just a photon from the solar wind can knock an electron off. And as soon as it gets a charge, then by law, it's required to start spiraling around a magnetic field, and that magnetic field is embedded in the solar wind and is moving out. So it becomes what's called a pickup ion at that time. And it gets carried out to this termination shock where we think it's accelerated to what we call anomalous cosmic rays, where we measure them. Now, this is a little tutorial on how that acceleration might take place. It's going to be a little movie. There's this little red dot here, which is going to be the particle that's getting accelerated. These blue things, you can think of as they're magnetic irregularities. I said that the particles travel on the magnetic field lines, but if there's a kink in the field or something, it gets scattered. It goes back and forth. And this is the termination shock, and the wind is coming fast here and then slows down abruptly there. And you'll see what happens to this little particle as it's bouncing around in there. So it hits one, another one, and then finally it's going to hit a head-on with a fast-moving one, and it's going to get a little bump there up in speed. And it turns out that from the particle's point of view, since this slowdown happens, it's like it's in between two converging walls. And it's bouncing back and forth, and each time it's getting a little boost in energy. And this is called Fermi acceleration, and it's named after Enrico Fermi, who first described it. Now, it turns out that particular method of acceleration is supposed to produce a distribution of energy of particles that we measure in a certain way. And we were looking for that. This is intensity of particles, in other words, low to high rate, essentially of count rate, basically. And this is energy low to high, or speed low to high. What happens in this shock acceleration is that there's more particles at low energies, and then right at the shock, and then it should fall off and then roll over eventually. And we were expecting to see this spectrum when we got to the shock, what we call a spectrum. But leading up to it, you'd see it build up to that. You'd see it unroll to that. Because the low energy particles have a hard time swimming upstream to where Voyagers are. So as you get close, though, you should be able to see this whole black curve. But that didn't happen. And this shows what did happen. This is each one of these is 52 days of data, just an average of a spectrum that we measured, similar to this over here. And the thing to notice is this bump in the middle is what we were looking for, is this little anomalous cosmic ray component. This low energy stuff is coming from the shock. This is locally accelerated particles from the termination shock. But we were thinking this whole thing would change and evolve like this as we went through. But you can see we went right through the termination shock. As time went on, that bump didn't change at all. We were astounded. And later on now, it did change. It did grow later on. But turns out that Voyager 2, if I showed this for Voyager 2, it did the same thing. And it's not even in the helix sheath. It's back in the solar wind. So that was for a different reason. So what happened? That is a very good question. And we're still trying to figure that out. There are three possibilities I'm going to mention. One is that a theory has come up that, well, maybe these particles, here's Voyager 2 and Voyager 1 near what we call the nose of the heliosphere, which is kind of compressed in like this. Maybe you only see the low energy particles there, and the really high energy anomalous cosmic rays come from the flanks, or even actually back here on the tail of the termination shock at the back end. That's one possibility. Another one is that maybe they keep getting accelerated as we go further into the helix sheath. We'll see a bigger and bigger spectrum. This was what we saw, this low energy part and then the hump as we went through. And then this is a model that says, okay, well maybe you'll get this at 100 AU, this at 120 AU, and then you'll find that it happens by what's called stochastic acceleration, which is just like that blue balls thing, Fermi acceleration, except it doesn't have the termination shock. It's just the turbulent medium itself can get you some acceleration. It's much slower, but this model says it might be possible. And then there's another possibility is that maybe we would have seen what we expected to see, except for the sun wasn't quiet. This is a model calculations over here on the left. This is density and distance. And this kind of shows you the situation. This is the pressure pulse from the sun. It's called a merged interaction region, so it's MIR on this plot. And it's not got to the termination shock yet. And so the energy spectrum at the shock is like that one the ideal one that we would see in this model. But once, 90 days later, or whatever this is, termination shock and the merged interaction region start to interact. Then you start to develop a little hole in the spectrum. And later on, it gets worse and deeper. And that is kind of what we saw. So that's why this is a kind of a semi-attractive model. In fact, there were lots of solar wind pressure pulses that came along here. These were actually measured on Voyager 2 in 2001. They sort of stopped here in 2004. There was one big one in 2006. But maybe if they quit coming, then this spectrum will regroup and reform itself in this pristine state. Maybe when Voyager 2 gets there, it'll all become crystal clear. It's not likely, but not impossible. Now, in order to understand this, the last final data plot, I need to remind you again that charged particles travel in a little helical fashion along the magnetic field lines. Magnetic field lines are like highways for charged particles. And I want to show you the magnetic field in question here is that of the sun. And that's shown here in the middle. We're looking down on the ecliptic plane from the north. And this, what happens is that the solar wind is going out, but the sun's rotating. And the magnetic field is embedded in that solar wind. So it turns out the magnetic field makes a spiral like that. And all the way out. And this is where Voyager 1 was in middle of 2002. That's the first time we saw particles coming from the termination shock. The termination shock is shown in purple here. And they were coming from the left, which was opposite the direction we thought. We thought when we saw them, they would come from the right because that's where this spiral line would intersect first, over there. But since we saw them from the wrong direction, we began, we think now that the heliosphere is not a sphere. It's not a circle. It's been pushed in on this side, something like this, so that these particles could come from the termination shock at 85 AU instead of, we know now it's at 94 AU. Now the termination shock could have been in motion too. That could complicate the picture. In the south, this is where Voyager 2 is in 2005. It's over here. And again, We think the termination shock is going to be about 85 AU, but we started seeing particles at 75 AU. And again, the similar kind of push-in by the interstellar magnetic field, we think, could cause that to happen. And so studying these kind of things help us determine the shape of the heliosphere. Okay, so I think we're ready to tackle this plot, which shows why we think Voyager 2 is approaching the termination shock and getting close. Let's just look at this first top plot. This is Voyager 1, some particle data showing intensity versus time. And there are two telescopes plotted here. I told you I had four, but in this case, we're plotting two that one looks along the field line one direction, one looks like along the field line the other direction. If you plot the ratio of those two, if it's 1.0, like here on this line, then there's no preferred direction of the flow. The flow is equal from both directions. But obviously, early on, the flow was not equal from both directions. It was coming from a certain direction, and that's the direction I showed you on that previous plot for Voyager 1. Now, Voyager 2, and you can also see here that it was kind of fluctuating around the intensity, but once it got to the termination shock right here, end of 2004, got real steady. It's been real steady ever since. On Voyager 2, we've got the same plot, and we started seeing them actually at 75 AU instead of 85 AU up here for Voyager 1, so that's why we think it's 10 AU closer at Voyager 2, the termination shock. But you can see that the intensity at Voyager 2 here is actually higher than it is at Voyager 1, even in the heliosheath. So we're saying any day now we could cross that termination shock on Voyager 2, and both of them would be in the heliosheath for a while. And the models also say that this is a model of the heliosphere, and this little light gray line is where they think the termination shock is at the position where Voyager 2 is in the south. And this is the trajectory. So this is distance versus time. This is trajectory of Voyager 2. And where those lines cross would be the estimated crossing, which would be soon, like maybe yesterday or something. And hopefully when the data gets collected from that crossing, we'll help answer the question, where were those ACRs when Voyager 1 crossed the shock? If I didn't tell you earlier, ACRs is short for anomalous cosmic rays. Okay, so here's an updated picture of the heliosphere with this push-in and all in there. And it shows where Voyager 1 is and Voyager 2. This is the trajectory they're going on, and the little arrow marks the point. We're past the termination shock on Voyager 1, about 10 AU. We're right near the termination shock on Voyager 2. And what we want to do is get to this little yellow-red transition where the space will be filled with matter from other stars and not the sun. And how long is that going to take? We think it might take another 10 years. That's what the models seem to say. And the electrical power should run, the latest estimate is 2025, or it should be plenty, because that'll put Voyager 1 at 170 AU, and that should do it. I was thinking, we're at the end, I'm out of armadillo jokes and everything, but I was thinking about what the real enduring legacy of Voyager might be. And is it all the great discoveries it made? Or maybe it's even something bigger than that. And I want to close with this picture and a little slideshow to follow, a short one, that was a picture that Carl Sagan lobbied to have taken. It was taken by Voyager 1 on Valentine's Day 1990, looking back. And he took what was called the family portrait, took a picture of a lot of the planets, including the Earth, from 4 billion miles away. And so I'm going to play a little video, a little slideshow that's narrated by Carl Sagan. I invite you to listen to what he has to say about this pale blue dot.
From this distant vantage point, the Earth might not seem of any particular interest. But for us, it's different. Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on the mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they can become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit? Yes. Settle? Not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Okay. Well, I was thinking, wouldn't it be great if we got the world leaders together to look at this slideshow and then have them turn to each other and say, you know, I think the man's got a point. And then world peace would ensue and global warming would be solved. The Voyager mission with the Nobel Peace Prize. Not likely, but not impossible. Thank you very much. Yes.
Yeah, by the way, that was great, the ending. I thought that was really nice. I just want to ask a question regarding the lifespan of Voyager. You mentioned now the calculations are that it will last until 2025. Mm-hmm. Is that best case, or is that sort of the best guess? Is that when energy will run out?
You know, that number has just moved up 5 years in the last few weeks. So I'm.
Why did that happen?
I am really. Jeff Hall is probably the one that could tell you the answer to that right back here. But.
Well, the RTD decay about 4.5 watts per year. And based on our current projections, the fact that the decay is slowed down, I think we have enough power to last to 2025. If everything else fails.
Yes, in the back.
Was there any discussion as to whether we should put a golden record on the Voyager craft?
Whether we should, we did.
Well, whether would have been a good idea if, say, these aliens found this thing.
Yeah. You know, it's interesting. There was a contest recently on the Voyager website that said if we're going to do this again, what should we put on it? Give us some ideas. And there were going to be winners. And I was reading some of those inputs, and some people thought we were out of our minds if we're not ready to defend ourselves if anybody comes, you know. But, you know, I think JPL Security will take care of them. Yes.
Why did you use gold instead of something else?
I think it's a thermal consideration. I'm not totally sure on that, but I believe that was the reason. Yes.
I was wondering, was it the Voyager's instrumentation or something else that determined that the magnetic pole axis versus the
Rotation?
yeah, the rotation axis on each of these different?
Uranus and Neptune, you mean? Yeah, it was Voyager. There's only spacecraft that's visited Uranus and Neptune has been Voyager, and it's probably the only one in a long, long time. I don't think there's any plans to go back anytime soon. Yes?
You mentioned an interstellar magnetic field.
Yes.
What generates the interstellar magnetic field?
Well, the galaxy has its own magnetic field. It's embedded in the arms and in the back.
Yeah, what that one gentleman said, I thought the same thing. You know, we're giving them too much information, but the second thought is it'd be trivial for any spacefaring race to just backtrack.
Yeah. Yeah, I think we're doomed either way. Yes.
How is the funding going for this? Is there enough funds to keep track of what's going on for the next 25 years or so?
Well, that's a good question because, recently, actually before Voyager 1 got to the termination shock, there have been movements to turn it off several times, and they have been averted. But what we go through on this mission and many other missions, are about, 13 or 14 missions, they're in what's called the extended phase of their life. They're not in the primary part of the mission. We think it's the primary part because this is really, for particles and fields, this is the most interesting part out here in the interstellar space. But we're considered an extended mission, and so we have to compete for funds with the other missions. And so we do this about every 2 or 3 years. We have to write a proposal, and we're just about to start to write another one. It turns out, though, that the last time we wrote one, Voyager Science was ranked #1 amongst all the spacecraft, so hopefully we'll get a good ranking again. Yes?
You plan to give the talk on the 50th anniversary of the mission?
50th anniversary? Yeah. How old am I now? That doesn't seem likely, but not impossible. Yes?
Okay, in your picture right here,
Yeah.
the bow shock is lit up. I'm guessing because the particles are, charged and all that kind of stuff. Do we have something like that? Is ours lit up?
Well, no, you wouldn't be able to see it from the. It doesn't have enough optical depth. You're looking right through it like that. I don't think. I wouldn't say you would. They could probably see it if they're looking back here. Yes.
Yeah, how long is the signal taking to get to Earth now?
It's a little over 14 hours from Voyager 1. It's a little shorter for Voyager 2. Voyager 2 is trailing behind Voyager 1. It's interesting, the distance to the heliopause may be shorter for Voyager 2 actually than Voyager 1. Voyager 2 might get there first, but it is traveling slower and it's also lagging behind Voyager 1. So it's a race. It's what we call the race to interstellar space. Yes?
Any surprises about the species of neutral molecules coming in that we know of? Mostly hydrogen, helium,
Well, that's actually, the discovery of anomalous cosmic rays had to do with someone realizing that the neutrals, the particles we would see would be the ones that are neutral in the interstellar medium. The ones that are easily ionized, like carbon, never get into the heliosphere. They go around our heliosphere. But the neutrals, so I don't know if you'd say that there's a little bit of a puzzle came up because the hydrogen seemed to be less abundant in the anomalous cosmic rays, but we think it has to do with how they're accelerated. So they're actually zeroing in very well on what the composition is from 2 different angles. One from measurements of these pickup ions and the anomalous cosmic rays, but also astronomers are able to calculate what it should be, and they're in pretty good agreement nowadays. Yes?
I'm just wondering, I think I saw the picture that the Voyagers are actually heading for the, I guess, the front end of the bow
The
shot.
nose, we call the nose, yeah.
Yeah, like so it was a sock. Now, was that specifically targeted prior to, I guess Voyager 2 was going towards Titan, and was that specifically thought of during the trajectory phase of the last planetary?
No, we lucked out in that case. Turns out, for example, Pioneer 10, for example, it went by Jupiter and Saturn, but it was a spinning spacecraft, so its resolution of the images were much poorer, but it's actually going down the tail. But it's long since no communication with Pioneer 10 of this. Power's out on it.
So it's just a fluke that you're heading towards the short end of the stick, as it were.
I believe it is, yes. Yes.
Has anyone been looking at the telemetry to see if there's a duplication of the Pioneer anomaly?
No, as it turns out, you'd never be able to find that on Voyager. Voyager's a 3-axis stabilized spacecraft. It's got little thrusters and gyros going on. And so those little perturbations in the Pioneer 10 anomaly are like a billionth of, it's too small an effect. It can do it because it's spinning, and it's not doing any thrusting or stuff like that. That's why it was able to be found, if it's even real. I'm not sure it is. A gravitational anomaly in what we understand by gravity. To 1 part in a billion, so it's a pretty small effect. Yes?
Was the mustache a dare?
No, we better not go there with the mustache. I got relatives in the audience here. Yes?
What can we expect to learn, or what are we looking to learn in the interstellar medium that might be different?
Well, one thing on our experiment, we measure not only anomalous cosmic rays, but also galactic cosmic rays. There are cosmic rays that come from the galaxy. And it turns out that the sun, by spewing out the solar wind and the field embedded in it, those low-energy galactic cosmic rays cannot reach us. They are excluded from the bubble. So they might be, so we don't know what the energy spectrum is of the lowest energy galactic cosmic rays, for example. That's one example. Yes?
I seen that when you did everything, it seems that they're going in the same direction, well, very different distance, right?
Yeah.
Are you guys thinking of sending one towards the opposite side, towards like the tail end, like a Voyager 3 or something?
Nobody's thinking of that. I'll tell you what has been thought of is maybe do an interstellar probe has been talked about for many years. And that would go much faster than Voyager and could get out in a much less time to these boundaries, but it just never has gotten the funding to get it really going.
Because Voyager is doing that job currently.
Well, it's doing, it's a sort of a exploratory spacecraft, and just like in the case of Jupiter and Saturn, they have now sent orbiters around Jupiter and Saturn, and they've really studied them in much more detail. Of course, no one has gone to Uranus and Neptune, and it doesn't look like that's in the works. So. Yes?
If you could take any equipment back 30 years that we have today, what would you have done differently? What would you include that we have now?
On the spacecraft?
Yeah.
Oh, boy, that's a good question. Well, there is a instrument that measures the pickup ions directly that has been launched on Ulysses and on ACE. And that instrument would have been useful on Voyager because the pickup ions there are many more of them further out you get. And we could learn more about those ions. Yes?
What is the function of the cameras on the Voyager now that it's beyond the planets?
Well, they're turned off. They could be turned on, but there's really nothing to look at. The last time we did something was 1990 with the cameras looking back at Earth. But in order to save power, we need to turn them off for the other instruments to use. And pretty soon, at some point, not pretty soon, but at some point, we're going to be sharing power amongst the instruments. The power is going to go down, and the instrument that takes the lowest power will be the last one standing.
What instrument is that?
Jeff would have to help me on that. I don't remember myself. Probably
We
not.
don't really have a power sharing plan yet, so
Yeah,
we
it's
don't
true.
really know what instrument will be the last one
Function.
on.
Yeah.
But that's TBD right now.
Yes.
Is it possible that any of these boundaries can damage any of the instruments?
No. These boundaries are very tenuous. As a matter of fact, you've got out there by far the best vacuum you could imagine. It's just a few particles running around per cubic centimeter. It's not very much at all. So no, there's no health hazard.
Are you surprised that your instruments have lasted so long?
Well, you know, not everything did last, actually. There is one instrument on Voyager 1, the plasma instrument, failed many years ago, and we had one of our detectors get blasted with radiation at Jupiter, and so we lost a front detector on one of those 4 telescopes. I guess from my experience with our own particular instrument, I didn't see why it wouldn't. If you works for a year, it ought to just work forever, because the solid state detectors we use don't seem to have any particular degradation. There is radiation damage that can occur, and a lot of that happened though near the planetary encounters in the radiation belts. Yes.
Where do we think the lowest energy cosmic rays come from? Are they coronal mass ejections or chromospheres of other stars? Any particular kind of star?
Well, we think they come from supernova shock waves. Other stars explode, they send out a shock wave, and that does this Fermi acceleration process and produces these cosmic rays. I should say, though, that there's been a lot of close calls with Voyager spacecraft itself in terms of, and it's an amazing tribute to the redundancy that was built into those spacecraft that we still were operating both of them at full efficiency. And it's also amazing to me how they can react to problems and fix them so quickly. They're just amazing. Yes?
Has the Voyager determined any unusual characteristics of the velocity of the solar wind at that distance? Does it change or vibrate or,
Well, the solar wind goes out pretty much at the same speed. It does vary with latitude. So if you're shooting it along the ecliptic plane, it's one speed, but during, this is a complicated story because it depends on the 11-year solar cycle, but during what we call solar minimum, where there are no sunspots, at high latitude it's much faster. It's twice as fast as it is here. So it goes from 400 kilometers per second, or 1 million miles an hour, to 2 million miles an hour as you go up to. But it's not very steady to begin with, but it doesn't fall off with distance until you get close to the termination shock. And then, of course, it abruptly changes. Although we're just measuring that for the first time right now. We're going to find out when Voyager 2, which has its plasma instrument working, goes through the termination shock. We're going to see what happens. Well, the theory says it should just drop abruptly, not all the way to zero. It still flows, and then it turns and goes around the tail of the heliosphere. That's what happens in the heliosheath. Yes?
Just like Hubble is able to see far better because it's above our atmosphere and it's useful as an astronomical instrument, could Voyager be used as something similar, and that it'll be out of our, it'll be really out there, and could it be looking at things that we can't see from anything that's in orbit or on Earth or anything like that?
No, those aren't big enough cameras to be like a Hubble or something like that.
I don't mean optical, I'm talking about the radio.
Oh, you're talking about like the cosmic ray instruments, what we call telescopes, which are little stacks of detectors. Could they do what now? I'm sorry, I was thinking about optical.
Could they detect extras? Could they detect things basically we couldn't detect here on Earth because of the fact that it's basically out of there all over?
Well, you just have to get out. You've got to get out of the atmosphere, and you need to get out of the magnetosphere of the Earth first of all. In the magnetosphere of the Earth, you can measure different kinds of particles, radiation belt particles, but to measure stuff in the interplanetary medium, you need to get out beyond that. And but once you're there, then once we get past the heliopause, we'll be able to measure low energy cosmic ray, galactic cosmic rays, like I said, that we can't measure today. Yes?
In terms of talking about the dips in the heliosphere that you said was a theory, was there any theory in terms of how much of that would be true, or what could be causing that movement, if it is movement in the heliosphere, or what could be causing those dips, why that would happen?
What were the
Instead of
dips
it just being a
again?
sphere?
The dips.
Yeah, dips in the heliosphere. Is there any theory as to why there would be dips instead of it just being pretty much a sphere?
Oh, you mean the indentation or the pushing? Yeah, there is a theory for why that happens. It has to do with the interstellar magnetic field, the magnetic field of the galaxy. It is a certain direction and shape. In fact, they've used this to tell how strong it is and which way it's pointed. And that can make it push in because it's pushing back. And we're blowing a bubble in that magnetic field and in the plasma of the interstellar medium. So there's several papers describing what that must be like. Yes?
You need the minimum speed to run away from the system, solar system.
Yes. Well
What
beyond.
is the source of that speed? Is that the fuel or the gravity and the gravity of the planets? But the gravity of the planet is within the system itself. So how can you run away from the system?
Well, what you do is when you go past the planet, you pick up the speed relative to the sun. And that's the important speed of getting out of the sun's system. So, yes, with respect to the planet, you didn't do much. But because the planet is moving around the sun, you do gain. And we got about a factor of, I think, almost 2 in speed from those planets. But I think it would have escaped anyway. I'm pretty sure. Just from the initial launch. Because we haven't been powering it since then, as far as that. That was just the initial launch and then these flybys of the planets give the speed. In the back?
Yeah. From all this travel from here to there, is any data that is secret?
Secret?
Yes.
No. No data is secret.
How do we know you're telling the truth?
Oh, you know what? I do need to do something. I need to correct something. I'm not in rehab, as a matter of fact. And, I was going to do this right at the end of the talk. And I hope this is on the webcast, because I want to thank my cousin-in-law, Glenn Wood, in Wichita Falls, Texas, for making up that photo of the rehab center for me. I don't want the people to go home and say, that guy's in belt buckle rehab. He's got some real problems. Well, I got real problems, but. Yes?
How many people are working on Voyager right now?
How many people? How do you get these questions? That's incredible. Well, there are like 5 experiment teams, and they each have a few people working on it. There's a spacecraft, which has a team of, I don't know, maybe a dozen people, something like that. It's way down from the time there were planetary encounters going on. I tell you, Jupiter and Saturn, there were lots of people working on it. But I think I've worn them out. One more?
Within the heliosphere, you had a spectral model, I believe, and there was one blue line that came out an arc above it. I was just wondering what that was, if there was a name for that, or what that was about.
It looked like
Oh, that's the current sheet of the heliosphere. Yeah, that's probably not an accurate model for the current sheet, actually. That separates the magnetic field of the sun, the 2 halves of it, north and south. Yes?
Is there still propellant or hydrazine on
Yes.
Voyager 1 or 2?
Yes, there still is. There's plenty of that. It doesn't propel it forward. It really is used to, to rotate it to a new lock star or something. Yes?
I have just a general question. For each spacecraft that's built and launched, does JPL keep a list of all the people, or not people, but companies that contribute to the building of the spacecraft and ultimate success?
Boy, you really asked the wrong person on that one. I don't know if is the right person here that could answer that question. I don't know. I really don't know. Would be a nice idea, because there's a lot of incredible contributions have been made, both in the spacecraft area and, of course, building the rockets. Okay. I think we're going to have to go. Thank you very much.
Frankly, you had pictures of Minovish and Flandra.
Oh, okay.